Okay, we're going to deal now with this integral here, right? Well, we have a problem here. The first problem is this integral here is not always positive. It's sometimes positive and negative because you have a cosine there. All right? Okay, but anyway, I'll show you that in this case, we still can say something about the convergence of this integral. The second problem is it is actually two improper integrals, right? One in minus infinity, one in plus infinity. So we have to analyze them separately, so to say. There's no other problem because the denominator is never zero. It's a polynomial and it's never zero. And the numerator is, of course, a continuous function everywhere. So this function is continuous everywhere. So there's no problem other than this integral is improper in the two limits. However, notice that this is the cosine. This is a cosine and therefore is an even function. And this denominator here depends on x squared, so it's also an even function. So the integrand is an even function and the interval is symmetric, which means that we can study this integral studying only half of it, because this would be twice the value of this integral here, cosine ax over k squared plus x squared dx. All right? If this integral here diverges, then so does this one, of course. If this converges, then this one converges too, and the value of this integral is twice the value of this integral here. So we just need to focus on this integral here. All right, so let's see what we can do. What we can do is, what we're going to do is to analyze what is the absolute value of this integral here. Because if we can find an upper bound to this absolute value, then we know that this integral converges, right? Okay, we know that this upper value, this absolute value is smaller than or equal to the integral of the absolute value of this function, which is the absolute value of the numerator here, plus x squared dx. Okay? But the denominator is of course positive, so there's no problem, right? So the only problem could be the numerator, and that's why we keep the absolute value there. And you know, of course, that the cosine is always smaller than or equal to 1 in absolute value, so you can get an upper bound for this integral here, right? So you get this upper bound for the absolute value of this integral here, all right? Okay, then we have to analyze what is the behavior of this function, but this of this integral here. But this is easy to analyze because on the one hand, we can just split this integral in two. We can just say that this is the integral from 0 to 1 plus the integral from 1 to infinity. Okay? And in doing that, we get rid of the 0 and we can do whatever we want, or we can replace the integrand by something equivalent because we focus just on infinity, right? This integral here is, of course, convergent. It's a Riemann integral. Okay, so there's no problem with this integral here. The argument is a continuous function in the whole interval, no problem. So it's this one that we have to analyze. And what we have to do is to see what the behavior of this function is when x is large. K is a constant, and by the way, k is never zero, so there is actually no problem at zero with this function here. But the reason we are going to separate this is because now that we will make the comparison, the integral that we're going to get, it is problematic at zero. So let's we separate zero to get rid of that problem. So we have this function here, and when x is very large, since this is just a constant, this behaves just as 1 over x squared when x goes to infinity, right? Okay, so all we have to do is to analyze what happens with this integral. Now you see why having a 1 here is important, right? Okay, because if we still had the 0, then this would be divergent at 0. Well, this is the integral of the reciprocal of a power, of a positive power of x, and we know that this integral, an integral like this, converges if this exponent is larger than 1, because this is of the first kind, right? which is the case because it's 2, so this one converges, so this one converges too. So this one converges, right? Which means that this integral here also converges, right? The value may be positive or negative. It's actually positive. The value of this integral is actually positive, right? But, well, anyway, it is a convergent integral here.